Let me wrap up our look at this relationship between science and society that we've been going through for the last few days. If you recall, the setting is the Italian port of Bari. During World War II, there's been a tremendous disaster there that's pretty complicated, but has some implications as far as biomedical science is concerned. There's a physician, Dr. Alexander, who has been assigned by the U.S. military to explore what has happened at Bari, and we've been taking a look at some of the aspects of that. We'll kind of wrap that up here today. And if anybody is interested in this really long but well done article, please let me know, and I can get it to you. So we'll just see where Dr. Alexander is now with respect to his thoughts on what's going on here. Alexander was fascinated by the idea that mustard interfered with the body's mechanism for producing blood cells, especially white blood cells. Because of the dramatic and reproducible effects, he could not help but wonder about the possibility of using the compounds directly or in some modified forms on human beings with diseases of the blood. If nitrogen mustard attacked white blood cells, perhaps it could be used to control leukemia, the most common type of cancer in children, with its unrestrained white blood cell growth, by using different dosages to destroy some but not all excess cells without annihilating the patients. But when Alexander proposed an ambitious set of experiments into mustard's medicinal properties, he was told by his chief, and then upon appeal by the National Research Council, that this was not the purpose of the Edgewood Laboratory. There was not enough time or money to pursue collateral lines of investigation that did not facilitate the national defense. He was ordered to put the project aside and return to his work on mustard casualty management, treatment, and decontamination. Chasing medical miracle cures would have to wait until after the war. On December 27th, 1943, Dr. Alexander submitted his preliminary report of the Bari Harbor catastrophe. It was immediately classified. Eisenhower and Churchill acted in concert to keep this finding secret, so there was no chance Hitler could use the incident as an excuse to launch a gas offensive. Any mention of mustard gas was stricken from the official record, and the medical staff of the British hospital in Bari was instructed to alter the patient's charts. Alexander's diagnosis of toxic exposure was deleted and replaced with the generic terminology for combat casualties, burns, lung complications, all other injuries and deaths due to enemy action. British officials never acknowledged Alexander's Bari report, but it garnered high praise from Eisenhower's senior medical advisors for the U.S. military. They lauded the exceptional job Alexander had done under challenging conditions, but told him that a commendation was withheld for fear of offending the Prime Minister. Nevertheless, Colonel Cornelius Dusty Rhodes, chief of the medical division of Chemical Warfare Service in the U.S., hailed Alexander's meticulous investigation as so complete and of such immense value to medicine that it represented almost a landmark in the history of mustard poisoning. Armed with the Bari report and the results of a top-secret Yale University trial that demonstrated for the first time that a regimen of intravenous nitrogen mustard in tiny, carefully calibrated doses could result in human tumor regression, the supervisor Rhodes went in search of funding to develop this experimental treatment, known today as chemotherapy. He persuaded Alfred P. Sloan Jr., the chairman of General Motors, along with the company's wizard engineer Charles Kettering, to endow a new institute that would bring together leading scientists and physicians to make a concentrated attack on cancer. On Tuesday, August 7, 1945, the day the world learned that an atom bomb had been dropped on Japan, the researchers announced their plans for opening of the Sloan Kettering Institute for Cancer Research. World War II was over, but the war on cancer had just been launched. And the Sloan Kettering Institute is still a very major research institute to this very day. So believe it or not, this article is still not over. There's more to it, but we'll terminate our look at it. And I think one of the fascinating parts of this, in a general sense, is this is a great demonstration of the challenges that exist as the scientific world and the non-scientific world attempt to communicate with each other and proceed forward. And there are often major pieces of dissonance between the scientific enterprise and the non-scientific enterprise, which complicates our world significantly. And I think this is a really sort of classic example of that, but certainly it had great relevance as far as our views on pharmacology is concerned. And we'll try to resurrect this a little bit when we get to cancer chemotherapy come second semester of the course. With that, I'll see if anybody has any questions or comments that you would like to make on this particular matter.
So is mustard gas or derivatives of it still used in chemotherapy today?
Slightly different forms, but yes, I mean, these are very toxic agents, and there are many other agents which are, a lot more specific and less adverse. But these so-called alkylating agents are still available for extreme situations today. And when we get to this segment in our course, we'll take a look at both of our textbooks have subsegments on cancer chemotherapy of alkylating agents. So that's a long answer to your question. The answer is yes.
Thank you.
Thanks for the question. Just another great example also of sort of the relationship between pharmacology and toxicology. And, in the chemical warfare realm, of course, we're thinking toxicology, but there are implications in many of these toxicological settings for therapeutic use in a clinically beneficial way too. And we'll see that as we get into autonomic drugs here shortly. All right, thanks everybody for your attention and questions. And if you have thoughts that develop as time goes on, please feel free to ask those. So we're within the final segment of our introduction to pharmacology and toxicology. And we just started a little bit on the push into pharmacodynamics, which is the science of drug action, and taking a look at some general principles associated with the measurement and analysis of the impact of drug substances on our bodies. And we'll be able to utilize, hopefully, be able to successfully utilize these general principles as we go through specific drug groups for the rest of the semester. So let's look into this a little bit here. Some of our burrowing owl friends. And I'm so easily taken off track, but it does remind me last night when we were right at dusk as we were walking the dog, we could hear the owls hooting over in the trees next to the creek. And boy, just as it was almost dark, a very large owl flew right over us, screeching a little bit. Probably looking at our dog is a small dog, and probably is pretty substantial prey for an owl like that. Fortunately, we didn't have anything like that, but it was gorgeous hearing and seeing the owls right as it was getting dark last night. hip shot was safely home. We talked a little bit about James and Bob yesterday as we were introducing this section. Bob is a really cute and very um, outgoing cat. And sitting on the streets of London, if you ever have a chance to take a look at that video, uh, Bob was an even greater attraction than James' music, I think. So just some review slides that I'm just going to move my way through here pretty rapidly. I think we were at about this point yesterday when we were thinking about the interaction of drugs with their targets, many times which are macromolecules, which we call receptors. The analogy of a key and a lock is somewhat useful, and also some additional terminology that doesn't really appear here, but I think you're already familiar with. In the interaction of a drug with the receptor, if that drug not only binds to the receptor, but is able to turn the receptor on, in other words, to access the ability of that receptor to alter things that are going on within cells, the drug is called agonist, agonist. If, on the other hand, the drug can bind to the receptor but does not have the informational content to allow that receptor to be turned on, so the interaction of the drug with the receptor is so-called silent, then those drugs are called antagonists. Now, in between the realm of agonists and antagonists are partial agonists. And partial agonists can turn on the receptor, but they don't have the capacity to do it to the full extent that a full agonist does. Now, there's additional terminology there that goes into greater detail beyond the realm of agonist and antagonist. And we'll introduce some of those pieces of terminology as we go along, but we'll just utilize that terminology that we have right now for the time being. This ability to turn the receptor on is raises a question of efficacy. And an agonist which can fully turn the receptor on uh, um, has the highest level of efficacy. And then that goes down from that into partial agonists, which have less than 100% capacity to do that. By the time we get to antagonists, in which there's zero capacity. Another piece of terminology that's often utilized in that regard is intrinsic activity. And full agonists have complete intrinsic or 100% intrinsic activity, whereas a full antagonist has zero intrinsic activity. The analogy of a lock and a key can be viewed perhaps if I were to drag out my keychain, there's a whole bunch of keys on that keychain, all of which fit into the locks in our school, but only the appropriate key has the ability to turn on the lock, for example, to get into a particular laboratory. So the binding event is analogous to the insertion of the key into the lock. And so there's informational content there, but not enough informational content to turn the lock or activate the receptor in the case of drugs in the situation where we've got an antagonist. So you might want to think about some of those analogies a little bit as we proceed throughout the year and talk about various types of drugs and their specific receptors. So not surprisingly, these interactions between drug and receptor can be analyzed using biochemical techniques and terminology. And this is where the relationship of drug receptor interactions uh, could sound very similar to the interactions of substrates with enzymes. They are parallel processes. They are exact processes in the cases in which the drugs themselves are capable of interacting with an enzymatic substance. So there, it's not an exact parallelism, but there's quite a bit of relationship between drug receptor interactions and Michaelis-Menten kinetics and terminology from enzymology. Basically, what this amounts to, and you can see in this simplistic equation here, we've got drug plus receptor binding to each other to form a drug receptor complex. That so-called forward reaction of the association of drug and receptor to form that complex is buttressed by a rate constant K1, the forward rate constant. The reverse of that, sort of the falling apart of that drug receptor complex to the initial forms of individualized drug and receptor is the is the opposite of that, or the dissociation constant. Uh, so in enzymology, that relationship is one in which the constant that's used to measure that relationship is called Km, if you remember, the Michaelis constant. And that's kind of analogous to the Kd, or the drug dissociation constant, here in the drug world. The difference is that the Km, since it's an enzyme, has kind of built right into it the sort of the efficacy part of it. In the drug world, it's a little bit different. And the association of drug and receptor to form the drug receptor complex is just that. It's an association. The drug could be an agonist, it could be an antagonist, it could be a partial agonist, but we're just talking about that affinity that the drug, whatever it is, has with the receptor, and not going on to whether the receptor is turned on or not. So therefore, the binding constant in the drug world is often referred to just as that as the binding constant, and you need to take another step beyond that to get to the efficacy aspects of it. But the binding constant aspect of it is very important in its own regard, of course, because you can't ultimately take the step to efficacy unless you have an association or binding of the two aspects with each other. So this is, a very important sort of matter in the world of pharmacodynamics, and we'll very much be referring to relationships like this within specific drug classes as we proceed throughout the rest of the semester. So we were already talking about this a little bit yesterday, in that drugs are informational agents that modulate cell function via drug receptor binding and ultimate alteration of the intracellular environment as a result of that relationship, at least in the case of agonists. In the case of antagonists, again, it's just the drug binding to the receptor. And the interesting pharmacology that comes about with respect to agonists, of course, is that since they're binding to the same locales on the receptors as agonists are, antagonists can compete for that binding site with agonists. At first glance, that might not seem to be much of a deal, but actually it's a huge deal. And if we take the opioids as classic examples, naloxone, which the public even hears about quite a bit in the news, is an example of a agent with zero intrinsic activity, and is a pure antagonist. But if an individual patient is overloaded with agonists like morphine or heroin at the binding site, that individual is in jeopardy of dying of overdose. Presentation of a high affinity antagonist like naloxone results in displacement of the agonist from that binding site and occupation by naloxone, which of course does not have any intrinsic activity. So that's a life-saving thing. And the ability of a pure antagonist such as naloxone to exert such effects very, very rapidly is one of the great things about opioid pharmacology. Unfortunately, not every drug group has a naloxone. And as we'll see as we go along, in some cases, it would be a great lifesaver if we had the pure antagonistic capabilities um, of a competitor like that in other drug categories. More on that as we go along um, throughout the year. So the KD then is an equilibrium constant. And this is, where this tremendous analogy exists between what you already know about equilibrium constants from the general realm of chemistry and applied to the specific realm of pharmacology here. So I always try to make a big deal out of the idea that KD is just another equilibrium constant. The difference being that the constituents are drug and receptor rather than just sort of more generic aspects of chemistry. So at the time in general chemistry, when you're studying equilibrium, sometimes I think we all go, wow, why are we spending so much time studying this? Well, here's an example right here of the relevance of the equilibrium uh, concept. And the really, remarkable thing, most remarkable thing about this to me is that drug receptor interactions, as we view them as pharmacologists and other pharmaceutical scientists, is attributable to the general rules of chemistry and physics, just like other equilibrium situations are. So it is so important for us to recognize sort of the general chemistry aspects of these specific drug receptor matters that we're covering here in pharmacodynamics. So we're looking at a ratio here of forward and reverse processes, as we've already talked about, and often the quantification of those particular matters occurs at the level of 50% occupancy of the receptor by drug, much as back in Michaelis-Menten kinetics, where if you remember, the KM is that point on the curve where you're halfway between no activity at all and V max, which was 100% activity. The beautiful parallels that exist in these various cases are something to really pay attention to. And again, it's tough for you folks who are so busy, but should you have the moment to take a quick look back at your chemistry of equilibrium properties, I think you would find it to be very useful. So the KD in the drug realm is an affinity constant. And again, sometimes it seems a little bit counterintuitive, but if you can achieve that 50% level of occupancy at a lower amount of drug than some other drug is able to do it, then the lower the KD, the higher the affinity. And the converse of that, of course, the higher the KD, the lower the affinity. So that's an easy place to get mixed up on, but certainly important to try to keep that straight. The whole realm of occupancy of receptors by drugs has been studied in detail over the last few decades. And as we sort of launched into the scientific era in this regard, sort of the realm of receptor occupancy was the first place that pharmacologists, molecular pharmacologists, studied. It turns out that in our outlook on drug receptor interactions in 2020, receptor occupancy does not provide all the answers for us. It, it sort of does from the standpoint of affinity, but not from the standpoint as you go beyond affinity into the realm of efficacy and what are the parameters that are involved in that regard. So we'll see some additions to the ideas of receptor occupancy as we go along. Well, of course, as quantitation-based scientists, we love to represent the information that is garnered from experiments by graphical means. And we've already talked about this a little bit, but let me just say a little bit about this particular drug receptor set of interactions that are occurring in this slide labeled Assessing Physical Drug Receptor Interactions. What might be a little bit surprising about this is that the green line there is specific binding, and that's typically, in a classical sense, a hyperbolic relationship. That's the sort of saturation, hyperbolic saturation phenomena that we've been talking about a little bit already. But the surprising part of it might be that there's a relationship that goes a little bit beyond that, and that's signified there in the red, called total binding. So the specific binding is similar to, but not exactly the same thing as the total binding. And the basic reason for that is, of course, that drugs are not perfect. They're no more perfect than anything else in our universe, in our quantifiable universe is. And so you'll notice down there toward the bottom of that graph that the blue line is a straight line relationship. That's called non-specific binding, or NSB. And that represents the imperfection of drugs in that they bind in places other than the specific binding sites on the receptors that we've already talked about. These other binding sites can be just about anywhere. They're often fairly small in number, yet recognizable in a quantifiable way. So if in a mathematical sense, if you subtract that non-specific or imperfect binding from total binding, you end up with the specific binding. And that specific binding is what we're interested in terms of the beneficial efficacy of drug substances. So the next graph here, entitled double graph entitled Drug Receptor Interactions Efficacy, goes on to show a dose-response relationship where on the y-axis, rather than just displaying the amount of binding, we're showing the actual ability of the drug to produce a pharmacological effect, which we're interested in the case of agonist drugs. And so this is where we get to a slightly different piece of terminology. The EC50 is the effective concentration, 50th percentile or median. Underlying this, of course, is the binding reaction that we just saw before, but this goes beyond to take a look at actual perturbation of the cell, much as in the realm of enzyme kinetics, the Km is the perturbation of the enzyme. Now, you'll sometimes see this represented in a slightly different fashion, and that is if you take the logarithm of the concentrations or doses on the x-axis as opposed to just the regular non-logarithmic mathematics of it. Often you transform your hyperbolic relationship into a sigmoidal one. And so this sort of S-shaped or sigmoidal curve is very frequently what you'll most commonly see represented. And the reason for the need to do that in a logarithmic sense in many cases is that we're looking at a very widespread range of doses that may range from 1,000 to 10,000 fold, somewhere in that range. And your dose response relationships get rather cumbersome to present that range of doses in the original form, whereas in the logarithmic form, that gives you a chance to actually visualize better what's going on. So some really important distinctions come up in the next slide called quantifying agonism. And you'll notice in the upper graph in this particular slide with drug X and drug Y, they are separated from each other on the x-axis. Now, they plateau at the same point. These two drugs in the red X and in the, I guess it's purple Y, differ in potency but not efficacy, because the efficacy is constant between the two. But on the x-axis, the relationship between the two drugs is represented by a shift to the right from drug X. So potency relates to differences in how much drug it takes to determine a particular dose-response relationship. Efficacy, on the other hand, in the purest sense, is not talking about how much drug it takes to do that, but it's talking about what impact that the drug has on the biological system. In other words, how effective is the drug at perturbing the biological system? These two parameters, potency and efficacy, are easily confused, and all of us at times talk about the power of a drug often when we're referring to potency, but the power of a drug really has to do with its efficacy and the ability to seek that power out relative to how much drug is a matter of potency. So potency matters are shifts on the x-axis. Efficacy matters are shifts on the y-axis. And I think you can see that graphically represented here. So you might want to think about that a little bit. That's often confusing stuff, and nevertheless very important stuff to differentiate these two
I've got a
critically
question real
important
quick.
processes.
Keith, I have a question.
Yes, go
So
right
back on
ahead.
another slide. So in the first graph, drug X would be more potent than drug Y because it takes less concentration of the drug.
Exactly right.
Okay.
That's exactly right.
Okay. And then the bottom graph for efficacy. So drug X is more efficacious than drug Y?
Yeah, and we could take an example of that one. For example, in the realm of opioids, drug X could be morphine, drug Y could be codeine, where we're talking about ability to relieve pain. And no matter how far you push drug Y, dose-wise, you can't ever achieve the level that drug X rises on the y-axis because of that difference in efficacy.
Thank you.
Yeah, you're welcome. Great question, and very, very important for us to think about ideas like that. And if we go up to the top graph again, if we think of drug X as being an agonist and drug Y being the same agonist but in the presence of an antagonist, we've shifted that relationship to the right. So we can use these things not only to compare one drug with another, but compare a given drug under different circumstances. And some of that will be confusing stuff, and particularly because I may or may not describe it as effectively as I should. It's important for us to keep these things straight. And questions like you had there are just great. And if anybody has those questions as we proceed, feel free to ask them, because it's almost 100% certain that other people in the class probably have the same or similar question. So this is just pretty much looking at the same sort of stuff that we've already talked about here, just a little bit bigger. Hope I'm going the wrong way. So this parallel shift of responses is what we were just talking about here in the last few minutes. And I don't know if there's anything more on this that I want to deal with right now. I want to emphasize the competitive aspects of agonists and antagonists right now. Some of this other terminology, such as non-competitive antagonism and so on, is stuff that I think is just designed to confuse us right now. I think I would confuse us more than help us out. So let's deal with the upper part of this slide in terms of competitive antagonism, such as what we were talking about with respect to naloxone and morphine, agents which are competing for the same site but having differences in intrinsic activity. In other words, only the agonist has the ability to turn that receptor on. The antagonist binds but doesn't turn it on. So if we think of all the keys in my pocket, they all fit into the lock uh, as agonists and antagonists do, but only the one key has the ability to turn the lock that I'm interested in at the time, just as only the agonist has the ability to, informational ability to go ahead and turn the receptor on in the drug case we're looking at here. So, uh, you know, you can analyze drug receptor interactions in a test tube. You can take those analogies all the way to the population of a living being, be it a laboratory rat or a human being. And so as you move more and more towards the realm of practical therapeutics, we start representing things on the y-axis differently. Now, on the x-axis, we'll still be utilizing changes in the amount of drug substance, typically referred to as dose when we're talking about an actual therapeutic setting, or concentration when we're talking about a more research-based setting, such as in a test tube. But concentration and dose are compatible concepts with respect to each other. But the difference really lies on the y-axis. And so when we're thinking about what's going on in a therapeutic setting, we want to know about the ability of actual human being patient to respond to those changes in dose. And so the y-axis looks different than it does in our previous look at dose response relationships. The really critical statistical point about these measures is if you look at the middle graph there, in the lower part of the middle graph, you'll see a Gaussian frequency distribution. The sigmoidal dose response relationships are really derived from that sigmoidal Gaussian relationship that you're so familiar with from your study of statistics. And so that transformation from a from a Gaussian relationship to a sigmoidal one is an incredibly important endeavor. Notice on the far right that with respect to the pragmatics of the clinical setting, we can compare effective doses in something that we want, such as hypnosis, which just means sleep, basically, with some adverse effects, which could be any adverse effect here. The most dramatic of these adverse effects being lethality. So your adverse effects curves are going to always lie to the right-hand side of your beneficial effect curves, or at least they better. If the two of them are superimposed on each other, for example, then the beneficial effects and the lethal effects would be identical to each other, and that's a very undesirable situation, as you can well imagine. the relationship of dose response curves from the adversity realm versus the beneficial realm are often referred to as the therapeutic index. And one of the most common forms of the therapeutic index is the one in which we're looking at median lethal doses in the numerator and median effective dose in the denominator. And so the larger the adverse doses are compared to the effective doses, the larger the therapeutic index will be. And so you want the therapeutic indices to be very large. They're not always really large. In the most desirable cases, they might be values of hundreds or even thousands, but in other cases, for lack of better drugs, more specific drug substances, the numbers will be much smaller. So the really critical impact of a slide like this one is the idea of the ratio that exists between adverse doses and effective doses. So the relationship between adverse doses and effective doses gets us into the risk-benefit realm of safety. Earlier, we were talking about the analysis of efficacious matters versus potency matters. So those are at least three important matters that can be dealt with as far as dose response is concerned: efficacy, potency, and safety. Well, there's, as we've been talking about really along the way, particularly with respect to our analysis of pharmacokinetics, there are many things beyond sort of the dose response realm that we've just talked about that can influence the effectiveness of a drug substance. And a number of those things are listed on this sort of catch-all slide. Many of these additional parameters, which we've already at least briefly talked about, and many others which we haven't talked about yet, but which we will as we go along. So now we're ready to bridge ourselves from sort of the general realm of dose responsiveness. The general realm of dose responsiveness has been available to pharmacologists, other pharmaceutical scientists, pharmacists, physicians, and other medical professionals for a very long period of time. But sort of the specific underlying aspects of that at the cellular and the molecular level have only become available to our view in recent decades with the development of available technology to measure these things at the cellular and molecular level. So now we're going to transition away from sort of the broader realm of dose responsiveness to the more specific cellular and subcellular realm of dose responsiveness and look at some parallel concepts as well as some new concepts that are useful to us at this level of interaction. So that's where we'll pick up when we meet again at 1 o'clock on Tuesday. We'll finish off this realm of pharmacodynamics, introductory pharmacodynamics at that point, and make our move into the specific realm of autonomic drugs and apply these principles that we've just been covering. Anybody have any questions as we depart for the day? Think about that for just a second. Let me wish you all a great Labor Day. Have a great time, but also be safe as possible. And see you all safe and sound again next Tuesday at 1 o'clock. Thanks so much. Best wishes.
Thank
You're
you.
welcome.